Now that we understand the optimal substructure present in shortest paths, we can follow our usual dynamic programming recipe to arrive at the basic version of the Bellman-Ford algorithm. Let's compile our optimal substructure lemma into a recurrence, a formula that says how the optimal solution value of a given subproblem depends on that of smaller subproblems. I'll use the notation capital L sub IV to denote the optimal solution value of the corresponding subproblem. Subproblem is being indexed by two parameters. One, V, that's the destination we're interested in this subproblem. And the second one is the budget I on the number of edges that are permitted in paths from S to V in this subproblem. So a few details. First of all, remember that in the last video we proved the optimal substructure lemma in general for general graphs G, which may indeed have negative cycles. For that reason, we have to allow cycles in shortest paths from S to V. We're not concerned about the cycle being traversed an infinite number of times because we have this finite budget I on the number of edges that we permit. I also need to explain what I mean in the case that there are no paths from S to V with at most I edges. And indeed, when I is very small, that will in fact be the case for many destinations V. So if there's no way to get from S to V using only I hops, we just define LIV to be plus infinity. And as usual, in the recurrence, which is going to be defined for every positive integer I and every possible destination V, we're just going to state that the optimal solution value for the subproblem is the best of the possible candidates identified in the optimal substructure lemma. That is, capital L sub IV, the optimal solution value for the subproblem with parameters I and V, is the best of all of the possibilities. So let me start with a minimum to take the best of the case 1 candidate and the case 2 candidate. The case 1 candidate is simple enough. One option is always just to inherit the best path we found from S to V that uses only I-1 edges or less. And case 2, you'll recall from the quiz at the end of the last video, really comprises a number of subcases, one for each choice of the final hop. So here we're going to have another minimum ranging over all possible edges WV. For a given choice of that last hop, the shortest path length is going to be the shortest path from S to that choice of W that uses at most I-1 edges. And then, of course, we also incur the edge cost of the final hop, W, V. Correctness, as usual, follows immediately from the optimal substructure lemma. We know these are the only candidates, and by the definition of the recurrence, we pick the best one. Because our optimal substructure lemma has been proven, whether or not G has a negative cycle, this recurrence is correct for all positive values of I, whether or not G has a negative cycle. So now let's see how it's useful to assume that the input graph G does not have a negative cycle. So we had a quiz not too long ago that discussed the use of the no negative cycles hypothesis. In particular, we argued that n-1 edges are always enough to capture a shortest path between S and any possible destination. Why? Well, suppose there's no negative cycles, fix a destination V, show me a path that has at least n edges. If it has at least n edges, then it visits at least n plus 1 vertices. There's only n vertices, so the path must visit some vertex twice. And in between two consecutive visits of a given vertex, that's a directed cycle. By hypothesis, there are no negative directed cycles. They're all non-negative. So if I throw out this directed cycle from this path, I get a new path to the same destination V, and its overall length has only gone down. Discarding cycles only makes paths shorter. That's why there's a shortest path with no repeated vertices, that is, with at most n-1 edges. So what does this observation have to do with our recurrence? Well, it tells us we only need to compute the recurrence, evaluate subproblems for values of I up to n-1. There is no point in giving a subproblem a budget bigger than n-1 edges if there are no negative cycles. It's not going to be useful. You're guaranteed to have already found the shortest path by the time I has gone as large as n-1. So to make sure this point is clear, let me just formally write down the subproblems that we're going to solve in the Bellman-Ford algorithm and which are going to be sufficient to correctly compute shortest paths for input graphs G that do not have negative cycles. The subproblems are simply to compute the shortest path lengths capital L sub IV. Of course, for all destinations, we're responsible for ultimately computing shortest path to every destination V, and for all relevant choices of the edge budget I. And so the base case is going to be when I equals 0, and we just said it has to go up as high as n minus 1 and no further. And this is actually a pleasingly parsimonious collection of subproblems. It may strike you actually kind of as a lot, because there's a quadratic number, right? There's n choices for the destination v, and then I is taking on n different values. But remember, unlike all of the other problems we've been talking about, the output of this problem is linear size. We're supposed to output a number for each destination v. So we really only have a linear number of subproblems for each statistic we're responsible for computing. And that's as good as we've had in any of our other dynamic programming algorithms. So now it's a simple matter to write out the pseudocode of the justifiably famous Bellman-Ford algorithm. Because our subproblems are indexed by two parameters, the edge budget I and the destination v, we're going to have a two-dimensional array A. Remember that we're measuring subproblem size via the edge budget I. That's sort of the great idea in the Bellman-Ford algorithm, to introduce this edge budget to control subproblem size. So the base case is when I equals 0, and then we're talking about getting from S to some vertex V using 0 edges. Okay, well, if V happens to equal S, then you can do it with the empty path, and the length of the empty path is 0. But if V is any vertex other than S, then of course you can't get from S to V using 0 edges. And remember, in that case, we define the optimal value solution to be plus infinity. So now we move on to our customary double for loop, one for loop for each of the indices that indexes our array A. And actually what's interesting is, unlike most of the dynamic programming algorithms we're discussing, here the order of the for loop matters. You cannot pick arbitrarily. You really need to make sure that you have all the smaller subproblems solved by the time you need them. That means the outer for loop should be indexed by the subproblem size I. So as we discussed, we're not going to bother letting I range above n minus 1. That's going to be sufficient in the case where there are no negative cycles. And for each choice of I, we solve all of the corresponding subproblems, all destinations V. For each choice of I and V, of course, we just write down in code the formula that we stated in the recurrence. So as I'm sure you recall, case 1 furnishes one possible candidate. It's always an option just to inherit the shortest path from S to V that you computed using only I minus 1 edges. Alternatively, from case 2, there's also one candidate furnished for each choice of the final hop. So for each edge that ends at V, for each choice W comma V, there's an option of taking a shortest path from S to W that uses only I minus 1 edges and tacking on that final edge WV. And as we've discussed, if it just so happens that the input graph G has no negative cycles, then this algorithm will indeed terminate with the correct shortest paths from S to all of the destinations. Those answers will be lying in wait for you in the biggest subproblems, the A, n-1 V's. So that's correctness. As usual, it follows primarily from the optimal substructure lemma, but in this case also the hypothesis of no negative cycles guarantees that taking I equal n-1 is large enough to actually capture the final answers. So we'll talk about the running time of the Bellman-Ford algorithm in a sec, but first let's just go through a quick example to make sure all of this makes sense.